This is MCT4C, day 13. This is our second day of translating trig functions. The 3-minute review is actually most of the lesson, and it's a bit of a calculator exercise. So if you don't get to this in class, you'll have to download the TI-83 emulator, or and install that. And hopefully I've talked about that in class, and if not, you can remind me to. But it asks us to investigate the roles of a and b in the functions a or y equals a sine bx, and the cosine as well. And so it says use a TI-83 or other technology to graph and complete the table. So other technology might be a graphing calculator app on your iPhone or something like that. But here's my calculator, and notice I got my window settings over here. And I'm not going to go through all of these. You can graph them. One word of advice, though, is probably I'd graph one at a time, one of these graphs at a time, and then add that to your sketch. So I've got sine x there, and if I graph that, this is the normal one anyway. It shouldn't surprise anyone. The dots are a little bit different, but not too worried about that. That we add that to our graph, whatever it happens to be, and we know important points in the normal y equals sine x are every 3 ticks, and then I add that graph, okay? And then, if you want, the next one can go, whoops, the next one can go underneath, and you could change it so it's thicker, so you can see the difference if you like, or whatever. What do we got? We got 3 sine x graph, and you see the difference. It's this one looks like the bumps are higher, right? It's been stretched vertically, and that makes sense because the 3's out front. It's not in with the x. So just like when we talked about the parabolas last day, review of earlier grades, that when the 3's out front and we're multiplying, it gets bigger, right? So, oops, and this was a mistake, wasn't it? I'm just going to erase that one. That was brutal. See, that went up to 2. You probably noticed that. So the normal one, the first one, should have an amplitude of 1, and the second one goes up to 3. On the next page, I've got sort of the final versions, but you should be able to go through this on your own. The interesting part, and I'll talk about this in a second, are these ones where the 2 and the 3 are multiplied in with the x, so we know something's going to happen horizontally. And I know your graphs look pretty crazy, but hopefully you did them one at a time so you can see which one is which, and we'll talk about how we filled out the table here in a second. The amplitude ones aren't so bad. We see that one that's got an amplitude of 3. The minimum and the maximum are stretched vertically, just like we would expect, and so we could see, state the new range if we wanted to. I'm not going to worry about that. We'll do that later. One thing I wanted to mention about the first sketches is this minus. That minus there meant we were flipped, right? And that calculator showed us that. Flipped vertically, and also since it's a half out front, it's squished vertically, so it doesn't go as high as the normal one. Now, the next sketches, the black one here is the regular cosine graph that we're used to, but then we threw a 2 in there, in with the x, this one right here, and that ended up with, which one was it? It was this red one. And hopefully you did a decent job sketching that. One way to think of this is how many cosine graphs, how many copies of the cosine graphs got in from 0 to 360? Well, do you see that there's 2? 1, 2, and that's kind of where that 2 is. And so when I'm thinking about the period, how long does it take for the graph to start repeating itself? Well, 0 to 360. Or 0 to 360, there's 2 of them. So I could say 360 divided by 2, each of the graphs had 180. or I could try and count up the ticks and go up to 180 and count the period as 180. Notice, and this is really hard to see on the graph, but it makes sense logically. If the period was cut in half, then the important points, which happened every 3 ticks or every 90 degrees on the normal graph, they also got cut in half. So that means on this red graph, the important point should happen every 45 degrees. Well, how much is 45 degrees? Well, 90 degrees is 3 ticks, so half of that's 45. 1.5 ticks, every 1.5 ticks. So my graph is a little bit off. I should have an important point right there, and then another important point there, another important point every 1.5 ticks. And I can see there that red graph starts repeating itself every 180. And this period change, this horizontal squish, as I called it here, kind of makes sense, because we thought earlier, anytime we put something in with the x, it does opposite that we think. We think multiplying by 2 should somehow stretch it out, but it's opposite. It squishes it horizontally, so that kind of makes sense. And that was reinforced the next one when it was 3x. 3x, I think on this one, is this purple one. And notice how many cosine graphs did we get from 0 to 360. There's 1, there's 2, there's 3. So what's the period? Well, it repeats every 120. 360 divided by 3, there's 3 of them in total. Each one has 120. Right? And that means the important points normally happened every 90 degrees, but if it was cut and squished by a factor of 3, every 30 degrees. 30 degrees is every tick. So these important points should have happened every tick. Well, every tick an important point. Every tick an important point. See, there's 120, 30, 60, 90, 120. It starts repeating itself, and every single tick has an important point because of this horizontal squish. Cool. The last one, the number in front of the x is a fraction. Well, we think a fraction should squish it, but in the direction of x, it's opposite. It's a stretch. And so, and in fact, when you graphed it, it looked like only half of the cosine function got drawn in from 0 to 360, and in fact it did, only half of it. So if I kept going, it would end up repeating itself after 720 degrees, right? This is y equals cos of a half x. Okay, so you can finish off your table, pause it, finish off your table. Hopefully you got that, and we'll sort of summarize our findings in the note. This was most of the lesson right here. On we go. Onward. Okay, so graphing sinusoidal functions 3, this is on page 30, and this is the stretches and squishes. Last day we were talking about translations, which are moves left and right and up and down, and now we're talking about stretches and squishes, and in fact flips as well. So from the 3-minute review, we can make the following conclusions. This graph is the normal graph stretched vertically. Well, which of these values stretched it vertically? It was A, because A affects Y values. So it's stretched vertically by a factor of A. That is, well, what's happened? It's changed the amplitude. Where the amplitude used to be 1, now the amplitude of A, excuse me. Good. Note, if A is less than 1, so if A is less than 1, so A was a half, for instance, then it's actually not a stretch, it's a squish. It's a vertical squish. We saw that in that last one. Squished vertically. This one, right? We saw that one. It was actually a negative, but the amplitude was less than 1. Well, it was a half, wasn't it? If A is negative, what happened then? Well, we had a reflection. Instead of going up first, like that, where the sine graph, we went down first. This is if the A value here is negative. And the fancy math word for flip is a reflection. And the reflection, the mirror, is in the x-axis, right? Okay. This box, this A, represents an amplitude change. So that's the, we talked about phase shifts and vertical shifts yesterday. This is an amplitude change. Number 2. So this graph with the B, what does the B do? The B changed the period, right? It squished it horizontally by a factor of 1 over B, right? So when B was 2, it squished it in half. When B was 3, it squished it in a third. That is, f at x has, well, it's got a new period, right? It's not 360 anymore. It has a period of, it's 360 and then divided by b, or times 1 over b. We went divided by b. So if we wanted to find out what the period of some function is, we took 360, which is the normal period, and divide by whatever values in with the x there. That was 2 and 3.5 in our 3-minute review. What's going to be important here, because the important points are how we actually construct the graph. We thought of the normal graph as an important point every 3 ticks. Well, they happen more frequently. They occur every 90 degrees divided by b. Or, we think of 90 degrees as 3 ticks, right? 3 ticks, 3 divided by b ticks, which is kind of a weird way to think of it. This is actually how we draw it, right? Recall that the normal sine graph has a period of 360 and important points every 90. So when we throw a b in with the x, then that changes the period and the number of important points. Notice if b is less than 1, like it was in that last one, like in y equals cos of a half x, then we get a horizontal stretch. But these rules still work, because when I divide by half, the period actually gets bigger. And it's a horizontal stretch. And this is called, friends, a period change. Okay, let me check my time, see if I need to break video. Yeah, let's stop there, and I'll go on to part 2 in just a